You snap a photo, apply a filter, and hit share. The interface gives you a satisfying checkmark almost immediately. But if you think about the physics of 500 million daily active users uploading gigabytes of data while querying relational databases simultaneously, that immediate satisfaction is physically impossible. The speed you experience is an illusion. It is the result of extreme architectural misdirection, pushing the heaviest computational work as far away from the central servers as possible. To understand how modern system design actually works, we have to follow the exact microsecond journey of a single pixel, from the moment it leaves the creator's phone to the moment it hits the scroller screen. Our journey starts with a user applying a heavy, vintage visual filter to a new photo. Sending raw images to a central server to calculate pixel changes would collapse the system. Thousands of uploads a second would melt the backend CPUs. Instead, the architecture shifts the burden to the edge. Local shaders hijack your phone's GPU, executing complex math locally. By forcing the client device to do the heavy lifting, the core backend expends zero computational energy on image editing. It only receives a highly compressed, optimized file. Now, that compressed image has to travel across the internet to the platform's backend infrastructure. If you try to drop millions of massive binary image files directly into a core relational database like PostgreSQL, the input-output loops will block and the entire database will lock up. The solution is decoupling media from metadata. The heavy image bypasses the database completely, going directly to an object storage bucket, which immediately copies it to delivery edge servers globally. The core database only receives a lightweight text string pointing to the photo's exact location. The platform protects its most vital organ by systematically refusing to actually store the photos it is famous for sharing. That covers how a post is written. But the real challenge is the read path, when followers open their apps to scroll. If the server had to query millions of posts, sort them chronologically, and cross-reference a complex web of follower relationships while a user waits, the app would freeze. Instead, the system relies on a push model, known as fan-out on write. The moment a photo is uploaded, the backend quietly pushes the post ID into a pre-computed cache for every single follower. When you open your app, your feed isn't being generated. It was already waiting for you, delivering a zero-latency scrolling experience. But this breaks down when you introduce the celebrity exception. Think about an account with hundreds of millions of followers. If the system tried to push a single new post into 600 million individual caches simultaneously, it would create a massive write amplification backlog and crash the update queues. The architecture uses a hybrid fan-out model. Celebrity posts bypass the push model, dynamically pulled and merged with your pre-computed cache instantly. As you scroll, cursor-based pagination locks the feed in place, ensuring you never see duplicate posts even as new data arrives. A seamless feed is never generated on the fly. It is a highly choreographed, pre-assembled illusion, custom-tailored to balance regular traffic with viral megastars. Looking at the complete architecture, the amount of work being done is staggering, but it is entirely decentralized. Your phone's hardware edited the photo. A delivery network holds the file. A hidden cache pre-assembled your feed before you even asked for it. You perceive a single omnipotent app seamlessly managing your digital life. Global system design isn't about raw server power. It's a massive logistical magic trick, performed so smoothly that the audience never sees the wires.